presenting this very interesting paper. I think beer is a bit more interesting than chemicals that I can't imagine what they look like. So this paper has to do with the relevance of oxygen for the formation of Strecker aldehydes during beer production and storage. But I will primarily be focusing on the storage part, not on the production part. Their main objective was to gain insight into the role of beer constituents and oxygen-derived reactions on the formation of Strecker aldehydes during beer storage. To get into this, I want to give some background information so we all understand what that main objective actually was. So we have ales, which are fuller-bodied and have a variety of fruit and malt aromas. These malt aromas are flavors like caramel, toffee, or nuts. The porters are a type of ale that are dark and have a fruity, dry taste. And stouts are like porters, they're also ales, but they're not as sweet, and they have a coffee-like character to them. Lagers are another type of beer that range from sweet to bitter and pale to black. And pilsners are a type of lager, and the pilsners and the lagers are what are used in this study because they don't have the dark malt aromas to them, so they can't cover up the taste and the flavor changes that are done. Some compounds that flavor beers. We have malts, which gives it that toastiness, and also browns the beers. The hops, which are the bitter, zesty, and citric flavors. And some compounds are esters, which give the fruity flavors like pears, roses, and bananas. The diacetyl, which gives the buttery flavor like popcorn. The enols, which give cardboard or light struck flavor, which is the skunky flavor you get. And the light will decompose the beer while it's being stored, so they like to keep it in darker bottles. And then there's the aldehydes, which gives somewhat of a green apple taste, and this is what we will be focusing on, is Strecker aldehydes. Strecker aldehydes are different just in the way that they are made, and they are named after the person who found them. And so Strecker degradation is the chemical reaction of an alpha amino acid turning into an aldehyde with a side chain and an imine intermediate. So, our main question is, does oxygen create flavor-changing Strecker aldehydes? Our main concern is the oxygen in the headspace of the bottle during storage. So what will we measure? We're going to measure the amino acid and oxygen concentration tested for their impact on formation of Strecker aldehydes during the beer storage. We also want to look at the de novo Strecker aldehyde formation during storage because off flavor is often associated with these staling aldehydes. And for those of you who don't know, de novo is the synthesis of a complex compound from a simple compound such as an amino acid. Another objective of ours was to look at the ROS pathway, which is the ROS-induced degradation of amino acids that yield Strecker aldehydes. This was it's a proposed pathway that they looked at, and they scrutinized it during their buffered model solutions. We'll look at those later. But reactive oxygen species, oxygen is very reactive, so it will gain an electron from other atoms such as iron, and it will become a radical. And this is part of the pathway that leads to the formation of the Strecker aldehydes. So as you can see here, we have iron giving an electron to oxygen, and this is now a free radical. And this is part of a bigger pathway of the entire pathway that we will see later on. But this is the iron recycling and creation of oxygen radicals. So before they could start, they had to quantitate the amino acids, aldehydes, and the oxygen radical levels in the beers before they added anything to it. I also want to explain what safe GCMS is because they use this to determine the Strecker aldehydes in the beers after storage for every experiment. SAFE stands for solvent-assisted flavor evaporation. It is the isolation of volatiles from aqueous foods, such as beers, and using the safe method results in higher yields from solvent extracts. The GCMS stands for gas chromatography mass spectrometry. It separates the chemical mixtures, the GC, and identifies them at a molecular level, the MS. So it'll take the mixture and separate it into individual substances by heating it, and then those heated gases will flow into the mass spectrometer. And then the mass spectrometer will identify the compounds based on the mass, and it will use a library that has thousands of masses. So their first experiment was to look at the influence of the oxygen barrier liner crown corks. These are the bottle caps that have the rubber lining on the inside, and it works to keep oxygen out of the bottle. So the samples were prepared in a glove box to control the atmosphere, and this controls the amount of oxygen that they have in the bottle while they're creating it. They use there's minimized oxygen entry using this crown cork because it's made from high-density polyethylene. So after 12 weeks, the structuraldehydes were analyzed using safe GCMS. From this, they found that these were the 5 main structuraldehydes that were produced. And as this first column is the reference of the fresh beers right after they were made, and this is the amount of the structuraldehydes. The second column is the reference of aged beers, but without the special cap on. And the last one is the beers with this cap on them. So you can see from the first line, there's an increase in production from reference fresh to with the liner on it, but not so much of an increase as with the aged. So this does tell us that there is diminished structuraldehyde levels by using these crown corks, so they do have an effect. Something else I wanted to get into was where these structuraldehydes came from. We're going to be talking about the 3 amino acids, leucine, isoleucine, and phenylalanine, and those will be the amino acids that they add to the beers. These first 3 are derived from leucine, and the last 2 are derived from phenylalanine. So as we can see here, this is 3-methylbutanol, 2-methylbutanol, methyl, phenylacetaldehyde, and benzaldehyde. So you can see the aromatic properties in these 2. That's where they came from. So their next experiment was to monitor the structuraldehyde formation as a function of these amino acids and with oxygen exposure. So they treated a Pilsner beer by adding 1 milliliter of these 3 amino acids. They had a reference by adding just 2 milliliters of water instead of the amino acids, so they would have the same volume of liquid in the beers and the same volume of headspace. The bottles were then closed by overfoaming to minimize the oxygen, and this is when you hit the bottom of the bottle and it overfoams, and the foam will push out all the oxygen, so then you cap it and you can minimize the oxygen that way. But the reference bottles were omitted from overfoaming because they wanted to see what the presence of oxygen would do. So when they tested the oxygen concentration right after capping, and the formation of structuraldehydes were monitored during 30 weeks of storage at 28 degrees Celsius in the dark. And they did this at 28 degrees Celsius and in the dark because they wanted to control for all the variables that could change the flavor of the beer. And light will degrade the beer, and temperature is also known to change the flavors. So what they found from this is that these 5 structuraldehydes all had an increase in production. As we can see again, the 3-methylbutanol went up 187%, 2-methylbutanol 55%, methyl 44%, phenylacetaldehyde went up 64%, and the benzaldehyde at most by 583%. So they were able to conclude that the addition of these amino acids and the exposure to oxygen clearly yielded an increase in these structuraldehydes. And this is an indication location of the de novo formation of the structuraldehydes. So again, that's going from the amino acids, either leucine or isoleucine, and phenylalanine, and those being made into the more complex molecule of the structuraldehydes that we see up here. The next experiment was to look at the impact of the total packaged oxygen. So they wanted to test different concentrations of oxygen and see if that made a difference. So they used a lager type beer again. And they prepared it in a glove box under nitrogen atmosphere to control for oxygen concentration while they were bottling it. They wanted to examine the potential de novo formation of the structuraldehydes initiated by reactive oxygen species, so they added phenylalanine D5. This is deuterium labeled phenylalanine, so in the end they're going to end up with D5 labeled benzaldehyde and D5 labeled phenylacetaldehyde, and they'll be able to look at the difference between those and the other beers without the D5 label. So they adjusted the glove box to different oxygen saturations, capped it with the crown corks, stored it again at 28 degrees Celsius in the dark for 12 weeks, and quantitated the structuraldehydes using safe GCMS. So this is one of the results that they found from this experiment. This shows the concentration of the two structuraldehydes, phenylacetaldehyde and benzaldehyde. And these two top lines with the squares are phenylacetaldehyde, and the bottom of the circles is benzaldehyde. The open symbols are with oxygen, and the closed are without oxygen. And there is no closed symbol for benzaldehyde because it didn't form enough for there to have any data points, so they didn't even include it on this graph. But as you can see in the difference here, there's a significant increase in production of this structuraldehyde with oxygen present. So they concluded that increasing the oxygen resulted in an increase in the amount of structuraldehydes formed during storage. They also found that exposing the samples to air spiking yielded a direct increase in the radical formation. And these radicals are what help lead to the formation of the structuraldehydes. Specifically, the D5 phenylacetaldehyde and D5 benzaldehyde were detected in the beers. This showed a clear dependency on the initial oxygen concentration before storage, as we could see that there was no benzaldehyde without oxygen. The emergence and increase of these two structuraldehydes is clear evidence for de novo formation during storage. This last experiment that they did is the model study. This is different than the previous experiment because they wanted to look at just these three amino acids. And with the other experiments, they had a whole bunch of different types of amino acids in it. So for this, they're controlling for which ones are in. They used a buffered model system, and this was to identify the role of the structuraldehyde formation from these three amino acids with only oxygen present. So the bottles were stored for 6 months at 28 degrees Celsius in the dark, and the structuraldehydes were again analyzed using safe GCMS. One of the original objectives from the beginning was to scrutinize the ROS-induced degradation of amino acids, yielding structuraldehydes in these buffered model solutions. So that's what we're going to find here. This is the pathway that we've been talking about, that I showed part of earlier. It is the pathway of the formation of these two structuraldehydes during storage, including the activation of oxygen, following ROS formation, iron 3+ recycling, and phenylalanine D5 oxidative degradation. So here we can see from before the iron recycling, which gives electrons to the oxygen to make radicals. Here we have the phenylalanine D5, and these are all the deuteriums labeling it. And then we have the oxidative degradation of this phenylalanine through here. And then up here is our amine intermediate. If you remember from studying what a structuraldehyde is, we need an intermediate. And then these last two are the structuraldehydes, benzaldehyde, and phenylacetaldehyde. Their results show these graphs. These are just 5 of the 10 graphs of the structuraldehydes that were formed. But these were the 5 that showed an increase in concentration with exposure to air. So the top 2 lines on every graph have exposure to air, and the bottom 2 lines are not exposed. So you can see the increase that air causes. So they were able to conclude that the ROS-induced pathway is responsible for the de novo formation of the structuraldehydes in bottled beer. And the air in the bottle headspace yielded an increased concentration of certain structuraldehydes. So here are all 10, and you can see on the bottom that these 5 didn't change like the top 5 did. So it's just certain aldehydes. So overall, in conclusion, this is the first time that evidence was found to support this mechanism for the ROS-induced oxidative degradation of amino acids, yielding a de novo formation of structuraldehydes during beer storage. It's a lot of words, so I hope you understand a little bit more at the end of the presentation. This does not imply, though, that this is solely accountable. So the existence and relevance of this pathway are supported by the importance of the radicals and the clear relationship between the structuraldehyde formation and total packaged oxygen. This study helps to further clarify food scaling mechanisms, particularly oxidative degradation of amino acids and formation of structuraldehydes during food processing and storage. For further study, the rest of the study that they did was on the effect of oxygen during the wort production. So it's also during the production, not just during the storage, which is also important for brewers to know. I'd like to thank Dr. Dave for being my advisor, and Professors Allison and Bobby Fleshman for helping me with this. Any questions?
Oh no, okay, ladies first. No, ladies first.
I have a question on the oxygen as a function of storage time. You had a really nice plot of the phenyl and the benzyl ones. Could you go back to that figure? Oh, deep. That, yeah. Okay, cool. This is looking at the concentration of each of those compounds with the various amounts of oxygen that they put in that controlled atmosphere. Is that correct? Or could you explain exactly what this is representing?
Yeah, this one is just whether or not there was exposure to oxygen when they packaged it.
Okay.
So they either exposed it to oxygen or they controlled for no oxygen in the bottle when they capped it off.
Cool. So either oxygen, atmosphere oxygen, or none at all.
Yeah.
Okay. So my question is, it looks like at age 6 weeks, there's a leveling off. Did they say anything, or do you think that that's because that there's this maximum amount of oxygen, so if its atmosphere is 20%-ish, is that right? I don't know.
Yes.
Cool.
Ish.
Or is that because, so why would there be a leveling off there?
So they talked about this a little bit, and they said that there is, the oxygen is the limiting reagent in this because there's only so much in that headspace. And then, like, while you're drinking it, it wouldn't be limiting because it's open to the air. But for this experiment, when they capped it and just left it capped and didn't change the oxygen concentration, it is the limiting reagent, so it'll stop at a certain point.
Cool.
Just to go off that, just to make sure I understand what they did. So they did only do the one oxygen atmosphere, or did they do multiple different concentrations of oxygen?
They did multiple different ones for, yeah.
Sorry, there's so much in this paper.
Yeah, this is only 10%.
percent of it.
multiple concentrations of oxygen, but that didn't have they didn't have graphs for that.
Okay, so they
So I
didn't
didn't have
indicate.
anything to show you for that one. But for this one specifically, it's just one concentration, like whether or not there was oxygen when you tapped it.
I guess that's a good thing that it takes, so like you said, if you open the bottle and you're enjoying it, the odds of Strucker aldehyde being formed, I'm assuming it's not going to take you weeks to enjoy the beer as it's
Right.
sitting there. So luckily
Yeah,
there'll be other problems if your temperature gets higher. That's really cool.
Yes.
So what's the sensory limit for like phenylacetaldehyde? So I mean, how much could be in the beer before I notice it? So I mean, is it so because we got a concentration of like it gets up to like 3.5 micrograms per liter? Would I notice?
I'm not sure about that specifically. I'm pretty sure they mentioned, or I read somewhere that it could stay up to like 6 months in storage, but I'm sure by then you'll taste it. I'm not sure.
What about, say, after 3 months of storage and just overall poor flavors that come about from personal tasting experiments that you may have done?
Yes, by then you would taste it, I guess.
Right, because it's.
Yeah.
I was so acetaldehyde has a threshold of 40 parts per million to notice the green apple flavor. So I don't know anything about Strucker aldehyde.
The diacetyl depends, because if you're really susceptible to diacetyl, you taste it like really, really low.
No, this is acetaldehyde.
I know, but
Yeah,
I'm just saying.
oh, sure. Oh, well, yeah, super tasters and all that.
diacetyl,
Yes, our super
You're gonna
taster
get-
right here.
You're all very interesting. You're in trouble.
You could be 10 parts
No,
per
the weird
million,
thing
and I
is
could be
diacetyl,
30.
I can't even taste it. That's why I love that butter so much.
Oh,
It's
there you
it's
go.
delicious.
So yeah, we could convert that into parts per million
It's the
real
same.
quick. Oh,
Yeah.
it is?
It's the same.
That is? Okay.
Micrograms per liter.
Okay, I always get confused. Thank you. That is parts per million. Okay, I was. Oh, good.
Right.
I wasn't going to embarrass myself, but that's I did anyhow. Good.
I have a question.
Oh.
Yeah, so, just thinking about, can you go back to the 10 graphs?
Mhm.
I'm sorry.
2.5 parts per million.
So, I mean, are there structural similarities? Would you expect these ones, based on their mechanism, to be less likely to form than more likely to form, the ones on the top versus the ones on the bottom structurally? Or was there any indication in the paper of that being something they expected to see?
I know that the ones on the bottom were derived from the leucine, isoleucine, phenylalanine. What do you mean?
I just mean, is there any trends with, did this make sense? Is basically what I'm asking.
I guess if you think that the top 5 were derived from the 3 that they added, then maybe the bottom 5 are derived from something else that isn't as reactive, I guess.
Or we'd have to add that, just to be able to see that.
I'm kind of annoyed with them in the furfural, is that how you say that?
Yes.
Look at the scale on that. You're like 2 orders of magnitude higher than almost anything else. The middle and bottom.
Oh. Oh,
Right. So,
yeah, the scales are all.
and then you look at the heptanal next to it.
Mhm. But I found the answer, at least for benzaldehyde. It is 350 parts per billion is the lower limit of sensory detection.
0.35. So, yep.
Okay. I feel better now. So the answer is yes, we can detect it. It's in the odor and flavor detection thresholds in water in parts per billion by
And this isn't
leffing
a
well.
filter, so you're not masturbating.
Right. But that was I'd never found it before. I found it.
Just, I can't envision it, so when you said they tested for oxygen after capping, do you have any better, how did they do that?
I think they used, was it ESR spectrometry or something?
The EPR was used, I think, for the oxygen radical to detect which oxygen was influencing the proposed mechanism. But I'm
Yeah,
They used some method
Okay, I was like, how did they do that?
I thought about that too.
Can you just go back to the mechanism so I can look at it more?
Yeah.
Sorry.
Sarah, I warned you, I was like, this paper has been promoting so much discussion. Dot.
I understand that it doesn't make any sense to be, yes, they are using gas phase notation, without a doubt, they're using gas phase notation, but that doesn't make any sense in a gas phase. Zero sense in a gas phase, particularly with the iron doing what it's doing. Like that iron doing that cycle, so unless they're really simplifying a very highly heterogeneous process, which all of the methods they're using, all of everything indicates to me that this is in that the O2 gets in there and then it happens, so you do an equilibration.
Actually, did they say anything about how, if it's the oxygen in the headspace that they're looking at, was there any sort of rate or looking at the solubility of the oxygen or how much oxygen was getting into the beer?
I don't think so. I know they kept, for one part, they kept it at equilibrium by keeping the oxygen concentration in the, wherever it was stored the same.
But that's with the cap on.
Yeah.
I have another question. Sorry, we're fascinated with this. So the oxygen caps, so it sounded like you were saying that there's like this oxygen barrier. Is it an adsorptive oxygen piece? Or is it on the cap, or is it keeping oxygen from coming in and then going through into the bottle? So is it a barrier, or is it a suck out any oxygen that could be remaining?
I imagine a barrier to keep oxygen from coming in.
Okay.
You have to try to get as much out before you cap it.
Cool. It scared me that day when I was actually understanding some of it.
Any other questions?
Sorry.
Oh,
No, we're done.
okay, let's thank our speaker. Okay, 20-minute break.